Hello everyone, myself Abhay Kumar. I welcome you all on this video lecture series on design of steel structure. Today we will discuss about rolled steel section and in this lecture we will continue our past discussion based on stress strain curve for mild steel. Then we will talk about test for notch toughness. Okay. Later on we will talk about the various rolled steel sections available or which are used in the steel structures, and in the last part of this lecture we will discuss about the various conventions suggested by our IS 800 2007 for member access. Okay. So, in this figure I am mentioned about I have shown a figure which is a typical stress strain curve of mild steel. Okay. I have also highlighted few major points which indicates the position of relatively change in the nature or material behavior. Okay. So, let us discuss and let us see how this figure comes while we apply tension force on mild steel specimen. Okay. So, if we will focus on this figure, we will see that it is plotted between the stress and the strain. As we will apply the strain, we can see the stress is varying linearly, okay, or we can say that stress is increasing. Okay. Now, if we focus on the nature of this line, we will find that it is a straight line. So, from here we can say up to from point O to A, the behavior of the material or the mild steel is linear. Therefore, this point A is known as proportionality limit. What does it mean? It means that at point A, the up to point A, the material will follow a proportional rule, that is the stress will be proportionally vary or linearly vary with the value of strain. For example, like strain will be proportional to strain. Okay. Now, if we remove this proportionality sign, then there will be a constant come, that constant is termed as elastic modulus. This constant will indicate the slope of this line. Okay. For most of the steels, this slope or this elastic modulus is very much constant. Now, let us see further. Now, if we will again increase the strain, then the stress will increase, and up to point B, the material will behave elastically. What does it mean? It means if we stress out our material up to point B, then after removal of the stresses, then our material will come back to its original position or will completely recover its strain or the applied strain. Okay. Therefore, this point B is termed as elastic limit. Later on, if we will again apply the strain, then our beyond elastic limit, our material will reach to its upper yield point. C dash is represented as upper yield point. At upper yield point, the material yields. Then again, if we apply the stress or increase the if we apply the strain or increase the strain, then the resistance from the material reduces, and this point is termed as lower yield point. For example, Fe 250, if there is a Fe 250, it is a grade of concrete which indicates the yield strength of the material, that is 250 Newton per mm square. Okay. So, where this 250 lies? This 250 indicates the value at the lower yield point. Okay. From C to D, our material behaves plastically. It means that from point C to D, there will be no increase in the stress as we continue apply the strain. Therefore, this region is known as perfectly plastic region or the yielding region. From point D, material again start to show the increase in stress as we increase the strain. Therefore, this region is known as strain hardening region. Okay. Up to point E, the stress value increases as we apply the strain. At point E, we reach the at the maximum resistance level of the material. This maximum resistance level is known as the ultimate stress. It is generally indicated as Fu or the ultimate stress value of the material. Okay. After point E, if we will continue increase the strain, then there will be reduction in the stress value or the resistance value from the material. If I draw if I draw the specimen which were used in the stress strain curve, that is the dumbbell shape, I talked about this in my previous lecture, then we will see then that there will be a neck formation in this region. I am zooming on this. So, at this particular level, the diameter or the size of the member will reduce and there will be a neck formation. Okay. Therefore, this region was known as necking region. Okay. Our material will look like this. Okay. Our specimen will look like this. Therefore, this region is known as necking zone. Okay. At point F, our material completely breaks out and we see this kind of a failure surfaces. Let me zoom this out. At the point of failure, we will find that there will be this kind of a surface when our material breaks out. This is because of the shear. Our material, we know that steel is a ductile material and it is weak in shear. Therefore, finally the failure occurs because of the shear. Okay. So, this is how our complete stress strain figure comes out, and these are the major points about the stress strain curve for the mild steel. Okay. Now, let us move to the next mechanical property of the steel, that is toughness. So, there are various tests which can be performed to determine the toughness value of steel. Mostly there are two tests which are commonly preferred to determine the toughness value. First is the choppy test, choppy V-notch test, and second is the Izod test. In this figure, I have shown about the choppy V-notch test. Okay. This is a machine in which impact testing machine, in which we can see there is a hammer attached in an movable arm. This movable arm is hinged at this very point. Sorry, at this very point. So, what we do, how we perform this test, how we calculate the toughness value or the energy stored in the material before failure. So, what we do, we release this arm from its starting position and it free falls by following this trajectory. Okay. While following this trajectory, the hammer converts its potential energy, that is this potential energy, amount of this energy, into the kinetic energy. At this very point, the the hammer strikes to the RA specimen and transfer its kinetic energy to the material, and this transfer of the force will be in the nature of impact. There will be an impact on this very point. Okay. So, this is in this figure I have shown about the how our material looks before the failure, or how our specimen looks before the failure, and after the impact we see that this kind of a failure we see. So, that amount of energy that this specimen will absorb for the failure, that can be measured from here. Okay. So, I told that this is the amount of the potential energy our hammer had. At this very point, the potential energy our hammer transfers to the specimen, and specimen breaks out at its toughness value. Okay. Then the left out energy, with the left out energy, this material or this hammer will go up to at certain height. Okay. So, the difference between the potential energy of these two points will give us the absorbed energy by this material, and this will be the toughness value of our specimen. Okay. So, this is just an introductory part. Okay. Through this it can be discussed in very much more details, but I just wanted to give you just an introduction about the toughness test we perform to determine the toughness. Okay. So, since the V notch toughness is mentioned in our mechanical properties in IS code, therefore, I discuss this. Okay. Now, let us move forward. Now, let us talk about the various rolled steel sections available in the market and how these are designated, how we should designate them, how we should mention them, okay, and what are the different series in which they are available. Now, let us talk about the very common rolled steel section available in the market. It is the I section. One may ask that why these sections are called as rolled steel section. It is just this came name from basically from their manufacturing process. We know that steel, these sections pass through the rolling mills, therefore, from there this term came into the existence, that is the rolled steel section. These sections basically defined or classified on the basis of their shape of the cross section. For example, this is a pen, and if we will cut from this here, this pen from here, we will see there will be a circular cross section. Okay. So, this steel section will look like this. I am trying to draw this in 3D. Okay. So, what we are showing, I am showing here, what I am trying to show here, I am trying to show here how it looks in the cross section. Okay. So, this I section, since it looks like the English letter I, therefore, it is termed as I section, and it is available in various series like ISJB. ISJB stands for the Indian Standard Junior Beam. Similarly, ISLB light beams, ISMB medium beams, ISHB heavy beams, ISW wide flange beams. What are these? LB, MB, HB? These are indicators of the weight. Okay. Light beam means that it will be in of lighter weight. Okay. Medium beam means its weight would be in medium range, heavy would have a higher weight. Okay. And wide flange beam would look like, for example, this would be our wide flange beam. Okay. Why? Because its flange is very much wider in comparison to the length of the web. Okay. So, these are the different series available, and how these are designated? These are designated by the series in which they belong and the depth. What is the depth? It is really important to designate any section. It is a very important property of the section that is shown here. Okay. It is the depth is the from upper point of the flange to the lowermost point of this flange is known as the depth of the section. Okay. So, how it is designated? Series followed by the depth in mm and weight per meter run, that is weight per unit length. Okay. So, it will be designated as, for example, ISMB, it means we are talking about Indian Standard Medium Beam. 500 would be the depth of the section, it is 500 mm deep at the rate of 0.852 kilonewton per meter, means its weight is 0.852 per meter kilonewton per meter of its length. Okay. One more thing I would like to highlight, that this portion of the I section is known as flange section and this section is known as the web section. Okay. So, the top section is known as the flange and the vertical section of the I section is termed as the web, and there is also a below point which is also the lower flange. Okay. So, from now onwards you guys must not confuse what is flange and what is web and what is the depth of the section. Okay. Now, let us move forward to the another type of section, that is channel section. It is also comes in various series, that is ISJC, Indian Standard Junior Channel, Indian Standard Light Channel, ISMC Medium Weight Channel, ISWB Indian Standard Special Channel. Okay. These are also indicated designated in the same set of rules like the series in which they belong, depth of the channel section and weight per meter run. Okay. ISMC, for example, series ISMC 300 would be the depth of the section which we are indicating at the rate of 0.351 kilonewton per meter, that is, it is the weight of the section. Okay. Now, in this we also have a flange and we have also a second flange on the bottom, and this would be the depth of the section. Okay. And this would be the web part of the channel section. Okay. One may see that channel section comes from the I section, or one may also say that it is a part of a I section. Okay. We will see this kind of section forming or combination of the sections in later part of the this design of steel structure series. Okay. Now, let us talk about the another very important or very common section, that is the angle section. This section comes mainly into two series, first in the equal angle series, another in the unequal angle series. What is the equal angle series? What is the unequal angle series? Equal indicates that the legs length of the angle section are equal. Unequal indicates that the length of the legs of the angle section are not equal. What does it mean? Let me show this to you by this figure. For example, this is an equal angle section. It means that the length of its leg would be same. Here is the unequal angle section. It means that one leg will be a bit longer or a bit shorter than the other leg. So, this is unequal angle section. So, in the indication for the angle section or for the designation of the angle section, we must mention the length of the legs through which the angle section is formed. Also, there is one more thing which is used for the designation of the angle section, that is the thickness of the legs. Okay. In most of the angle section, generally the thickness of both the legs are constant. Okay. So, how it is designated? It is designated through like ISA, it means Indian Standard Angle 150, 12 mm thick, or in the same sense we can say 150 cross 150 cross 12. What does it indicates? It indicates that one leg of this angle section has the length of 150 mm, second is also of 150 mm, and the thickness of the angle section is 12 mm. For unequal angle, it would be like 150 cross 115 and 10. What does it indicate? It indicates that one leg is of 150 mm length, second is of 115, and the thickness of it is 10 mm. Okay. These are really very common sections which we can commonly see in various steel structure around us. Okay. Now, let us look at another section like T section. Okay. T section has one flange only and a web now, but there is not another flange at the bottom of the T section. It looks like English letter T. Okay. So, in this figure I have shown a typical T section, it is a flange, it is a web, okay. And in this the depth of the section is also really very important, okay, indicated by H, okay. Okay. Now, this T section also comes in different series like ISNT. ISNT stands for normal T, ISST stands for heavy flange T, ISSSLT stands for standard spatial legged T, and similarly ISLT, ISJT. Okay, you guys can read it from here. How it is designated? It is designated by the same set of rule that we used in I section, that we used in the channel section, and so it is designated like the series ISNT. For example, it is taken the section which we are designating here is from the normal T series, okay. Then ISNT 60, what does it mean? It is the depth of the section. The T section which we are talking about is of 60 mm deep, okay, at the rate of 53 Newton per meter. What does it mean? That its weight is 53 Newton per meter of its length, okay. One more thing I would like to mention, that it is a term TF, it is the term TW. What does it indicating? It is indicating the thickness of the web section and thickness of the flange section, okay. We will use these thickness in later part of the section, okay, later part of the series, okay. Now, let us move forward for the other type of steel sections or rolled steel sections available in the market, but these are not very much commonly used. Sorry, these are commonly used, but we would yes. What I was talking about? I was talking about, let us look at other common available sections, okay. This is a bulb angle section. What does it mean? It means it has a bulb shaped structure at the end of one of its leg. It is mostly used in the ship building industry. We have various kind of bars section available. It is a tube section, it means it has a hollow tube, okay. This is a thin shell kind of a structure, okay. It is a circular section, square section, okay. So, there are various bars come in the market, okay, with these kind of section. Also, there are various flats or the sheets come in the market, okay. Strips of steel sections come in the market, okay. Now, let us talk about the built up section. Why? What is built up section? As its name indicates, this section is built up. What does it mean? It means it is a combination of two different sections already available in the market. Why do we need to make a built up section? We need a built up section to increase the capacity of the member. For example, there is a beam and this beam is subjected to very heavy load, okay. Therefore, the stresses will be very high at this very point. For this figure is not right, very high at this level. So, to increase the resistance level at these very points, we must increase the load carrying capacity, and what we are doing? We are providing cover plates at the I section. Similarly, welded plate girder, for example, the depth of the available of the I section in the market is very less, okay, and if we are constructing a beam which requires very high depth. So, how we will construct this our specially required beam? Okay, we will construct our specially required beam by connecting two different kind of plate section like this. Similarly, double angle section and double channel section can be joined together in this manner to support heavy loading. Now, let us talk about the conventions for the member axis which are suggested by the IS code. Okay. So, as per clause number 1.8, axis should be that axis which should is along the length of the section. Okay. So, for example, there is a beam, please visualize with me, this is a flange, this is the web and this is the again flange. So, the x axis will be along the length of the section. Okay. YY section is the perpendicular to the flanges. Here it is shown. Okay, YY section is shown as the perpendicular to the flanges. Similarly, ZZ axis is axis parallel to the flanges. Okay, that axis which is parallel to the flanges is termed as the ZZ axis, and that axis which is parallel or perpendicular to the flanges will be termed as Y section. Okay. Now, let us talk about the these axes in the angle section. Okay. So, from angle section, the perpendicular to the smaller leg will be the Y axis, and axis parallel to the smaller leg will be an ZZ axis. There are two another sections are also mentioned, that is the UU and VV sections. What is UU and VV? Let me select this. Okay. What is UU and VV? UU and VV are the major axis and the minor axis respectively, and these are these are of different value in angle section. Okay. In I section or in channel section, the x axis and y axis, y axis and z axis are the major and minor, and in angle section we require another designation, therefore it is mentioned like this. Okay. We will discuss this we will continually discuss all these in later part of the course. Okay. Thank you for that today.